Bridge rectifier. This is the bridge rectifier diagram. Now, if we observe here, input AC is applied through the centered step-down transformer. This step-down transformer is used to reduce the voltage. Here it is 230 volts. To reduce this voltage, we are using this step-down transformer. But here the step-down transformer is not mandatory. Directly, AC signal can be applied to the bridge. AC signal can be applied to the bridge. So in the case of half wave and bridge rectifier, transformer is not mandatory. But in the case of full wave center tap rectifier, so there the center tap transformer is mandatory. Now, four diodes are connected in the bridge form, and the load is connected between the uh, cathode to the anode, and here coming to the working. So if the full sine wave is applied, then how we are going to get this two positive half cycle? We will try to analyze now. So here, if it is a, if this signal is, now this signal here I am showing it. So now here, if the positive signal is there, if the positive signal is applied to the point A, then this is applied to both D4 and D1. So with this, D4 becomes a negative forward reverse biased, and D1 is forward bias. And now the signal will flow through the D1, and here signal will come. This signal again makes this D3 with the reverse bias. So this signal will flow through, this current will flow through the V out, and it will come again like this. But here already D4 is reverse biased, so it will flow through the D2 and to the centered to the step down transformer. So here, if you see the current direction for the positive half cycle, diode D1 and D2 both are forward biased, and the current is flowing in this direction. It makes positive here and a negative. So thereby we get the positive half cycle across the load due to the diode D1 and D2. At the time, D3 and D4 both are in reverse biased. Similarly, if the negative signal is applied, what happens? You will see. If the negative signal is applied over here, so we can analyze with the negative signal, or if you wanted to analyze with the positive signal, that can be done by the, if the negative signal is available here, that time the positive signal is here. So that time diode D3 and D4 both are forward biased, and D1 and D2 both are reverse biased. Now, if you see positive is applied over here, then this makes diode D2 reverse bias and D3 forward bias. So D3 to current will flow like this. So it is making positive and negative again, and it is coming. So here it is coming like this. And for this positive half cycle, already this diode D2 is reverse biased. D4, it will flow through the D4. And this positive signal makes again diode D1 reverse biased. So signal will go to the transformer. When this positive signal, when the positive signal is coming over here, that time this makes the diode D1 reverse biased. So it will flow the current in this direction like this. So with that, one more, if you observe the polarities, again it is a positive and negative. So it provides the one more positive half cycle, that is due to the D3 and D4. So, and this repeats. And if you wanted to analyze with the negative half cycle, instead of taking the positive half cycle over here, if you wanted to analyze this for the second half cycle, So how to do that? So in both the ways you can analyze. When negative half cycle is over here, that time positive will be there and we analyze like that. For this negative half cycle, what happens, we will see. So through the resistor, if positive current is flowing, it makes positive first and it makes negative. If the negative current is flowing, then it makes negative and after that it makes positive. So if you have the idea of this, then if the negative half cycle is applied at point A, so it makes diode D1 reverse bias, D4 forward bias. So current is coming like this. And for this negative half cycle, again, D2 is reverse biased. So it will flow in this direction. It will flow in this direction and it is going up. But this is the negative cycle. Negative current is flowing up. So it makes first negative and next positive. It makes negative and positive and it comes here and already diode D1 is reverse biased. So it will flow through the diode D3 and goes to the transformer. Again, if you see here, the polarities are plus and minus only. So with that, we will get the negative half cycle, one more positive half cycle for the negative half cycle of the input due to the diode D3 and D4. So this is the second analysis. Either you can do the, when negative half cycle is there, at the time positive half cycle is here. So you can do the analysis for the positive cycle or you can do the analysis directly for the negative half cycle. This is about the working of the bridge rectifier. Now, coming to the analysis, already we have calculated the VRMS for the full cycle. This is Vm by root 2 and VDC is 0. Now already this in the full wave rectifier we calculated the, now here the time period is how much? 0 to pi. So frequency is 100 hertz and time is reduced to half. Here frequency is 50. So time period is 0 to pi only. So for that VRMS, if you calculate, that is Vm by root 2 and VDC is equal to 2 Vm by pi. This already we have derived in the full wave rectifier. The same analysis you have to apply over here. And coming to the ripple factor. So ripple factor already that derivation we have done for the full wave rectifier. The same derivation here we need to use. It is 0.482 and efficiency is, percentage of efficiency is 81.2%. This efficiency also we have derived in the full wave rectifier. The same derivation is we have to take to bridge rectifier. Now coming to the transformer utilization factor. Now here, when we are using the transformer, that time here the primary side and secondary side, both are single winding is there. So that's why you no need to take the separate tough for the primary, separate tough for the secondary. Any one of the tough we can calculate. That is the tough for the bridge rectifier. So now here if I'm calculating the tough, so PDC is equal to VDC into IDC divided by VRMS into IRMS. So now VDC is equal to 2Vm by pi and IDC is 2Im by pi. And what is VRMS and IRMS? So this is the input signal. And for both the signal, the current is flowing. So this is the current. Current is flowing for both the half cycles. So here we have to take Vm by root 2 and Im by root 2. Here dissipated and rated, both are same. If you calculate this, 0.812. This is the transformer utilization factor for the bridge rectifier. And this is a more in the case of bridge rectifier. Now coming to the peak inverse voltage. So already I have explained that. So when the reverse bias is applied, now here if you see what is the current flowing direction. So I am taking any one of the direction, either this or using D3 or D4 you can take. So this is the current direction. Now for this loop, we need to apply the KVL. So Vs, whatever the voltage is applied across the transformer, Vs is equal to D, Vd. So across the D1, Vd plus V0 plus one more diode. So Vd. So when the negative cycle is applied, now if this is the waveform, then negative for the negative half cycle is applied. That time minus Vm is applied So VD, we need to calculate the voltage drop. Now for the negative half cycle, what happens? D3, D4 are conducting and D1, D2 are not conducting. At the time, what is the voltage drop across the D1, D2? That we need to find out. So we do VD plus, and because of two diodes, so current is flowing and voltage is available across the load. So here we need to take VM is equal to, V0 is equal to VM and VD. So 2VD is equal to minus 2VM. So VD is equal to minus VM. This minus indicates what? Reverse voltage. And what is the magnitude? It is a VM. So in a bridge rectifier, how much the PIV is? VM. So this is the comparison table for the half wave, full wave, bridge rectifier. All these we have derived. So PIV we derived. VM, it is in the case of half wave rectifier, 2VM in the case of full wave rectifier, and again in the bridge it is a VM. So again, like that, so ripple factor we derived, and ripple frequency. So this is the input frequency, that is 50 hertz, and this is the half wave rectifier, and this is the full wave rectifier. So in a full wave rectifier, time period is reduced to half. That's why here the frequency is 2f, and in the case of full wave, both bridge and full wave, it is 2f, and half wave, if you see, the time period is same as the input, so frequency is also same, and efficiency also we have calculated for the three, and tough value also calculated. So this is the comparison table. And VDC output at no load is nothing but what? VDC we have calculated for this value, and for this value we have calculated the VDC, that is VM by pi, 2VM by pi, and 2VM by pi. So this is the comparison table. With this rectifiers without filter is completed. Now here if you observe, this waveform is not a pure DC. Some AC content is present. So to get the pure DC, we need to connect the filters. That I will explain in the next lecture.